We have learned a great deal about our universe. In the course of the centuries, we have come to realize just how many wrong ideas we had. We thought that the Earth was flat and that it was the still center of the cosmos. We thought that the universe was small and unchanging. We believed that man was a breed apart without kinship to the other animals. We have learned of the existence of quarks, black holes, particles of light, waves of space, and of the extraordinary molecular structures in every cell of our bodies. And the more we discover, the more we understand that what we don't yet know is greater than what we know already. We keep learning. If we try to put together what we have discovered about the physical world in the course of the 20th century, the clues point towards something profoundly different from what we were taught at school. An elementary structure of the world is emerging, generated by a swarm of quantum events where time and space do not exist. This new world is slowly emerging from the study of the main open question posed today in fundamental physics: quantum gravity. This is the problem of coherently synthesizing what we have learned about the world with the two major discoveries of 20th century physics: general relativity and quantum theory. Some of our most recent ideas draw on concepts and issues first introduced thousands of years ago. The connection between problems posed by the scientists of antiquity and solutions found by Einstein and contemporary researchers into quantum gravity is surprisingly close. From the earliest times, or at least since humanity left written texts which have come down to us, people have asked themselves how the world came into being, what it was composed of, how it was ordered, and why natural phenomena occurred. For thousands of years, answers referred to elaborate stories of spirits, deities, imaginary and mythological creatures, a colourful but ultimately monotonous flow of stories about plumed serpents and great cows, irascible, litigious or kindly deities who create the world by breathing over abysses, emerging out of a stone egg, or simply uttering fiat lux, let there be light. Then, at the beginning of the 5th century BCE, in the busy, prosperous Greek city of Miletus, a group of thinkers led by the philosopher Thales and his pupil Anaximander reformulated the way questions were asked about the world and the way answers were sought. The Milesians understood that by using observation and reason, rather than searching for answers in fantasy, ancient stories, or religion, and above all by using critical thought in a discriminating way, it is possible repeatedly to correct our world view and discover new aspects of reality. This was the dawn of science. Perhaps the decisive discovery was that of a different style of thinking, where the disciple is no longer obliged to respect and share the ideas of the master, but is free to build on those ideas without being afraid to discard or criticize the part that can be improved. From this moment onwards, knowledge begins to grow at a vertiginous pace, nourished by past knowledge, but at the same time by the possibility of criticism, and therefore of improving knowledge and understanding. Within a matter of a few years, Anaximander understood that the earth floats in the sky, and the sky continues beneath the earth, that rainwater comes from the evaporation of water on earth, that the variety of substances in the world must be susceptible to being understood in terms of a single, unitary and simple constituent. He calls it the apeiron, the indistinct. He also understood that animals and plants evolve and adapt to changes in the environment, and that man must have evolved from other animals. This was the first germ of physics, of cosmology, astronomy, meteorology, of biology. Rough and elementary, but in the right direction. From Miletus, around 450 BCE, a philosopher called Leucippus embarked for the city of Abdera. Little is known about him, except through the work of his brilliant young disciple Democritus, whose long shadow was to be cast over the thought of all subsequent times. Together, Leucippus and Democritus built one of the most spectacular achievements of ancient thought, the majestic cathedral of ancient atomism. Their idea is simple. The entire universe is made up of a boundless space in which innumerable atoms race. Space is without limits, without a centre or a boundary. Atoms have no weight, no colour, no taste. They are indivisible. They are the elementary grains of reality that cannot be further subdivided, and everything is made of them. They move freely in space, colliding one with another. They hook onto and push and pull each other. Similar atoms attract each other and join. The infinite variety of the substances of which the world is made derives solely from this combining of atoms. Just as by combining the 20 or so letters of the alphabet in different ways we may create comedies or tragedies, stories or epic poems, so elementary atoms combine to produce the world in its endless variety. It's an immense vision, boundless, incredibly simple and incredibly powerful, on which the knowledge of a civilization would later be built. Democritus wrote dozens of books dealing with questions of physics, philosophy, ethics, politics, and cosmology, anticipating by some 2,000 years the best aspects of the 18th century Enlightenment. All these books have been lost. We know of his thought only through the quotations and references made by other ancient authors and by their summaries of his ideas. I often think that the loss of the works of Democritus in their entirety is the greatest intellectual tragedy to ensue from the collapse of classical civilization. At the end of the 4th century CE, Emperor Theodosius declared that Christianity was to be the only and obligatory religion of the empire. The closure of the ancient schools, such as those of Athens and Alexandria, and the destruction of all the texts not in accordance with Christian ideas, was vast and systematic. It was not for another 1,000 years, when Greek learning was returned to the West by Persian and Arab scientists, that scientists like Copernicus, Galileo, and Johannes Kepler restarted the adventure of knowledge and began to make the leaps forward that led to modern science. Since then, it's been an increasingly rapid journey. In the 17th century, directly inspired by ancient atomism, Isaac Newton explains the reason why things fall and the planets turn. He imagines the same empty space as Leucippus and Democritus, where elementary chunks of matter race, but also the existence of a force which draws all material particles towards one another. He calls it the force of gravity. It is thanks to theories based upon Newton's equations that today we build bridges, trains and skyscrapers, engines and hydraulic systems, that we know how to fly planes, make weather forecasts, predict the existence of a planet before seeing it, and send spaceships to Mars. It seemed that the final key to understanding reality had been discovered. The world consists only of a great, infinite space where, as time passes, particles move and attract one another by means of forces. But Newton knew that his equations did not describe all the forces that exist in nature. There are forces other than gravity that act upon bodies. Things don't move just when they fall. The problem left open by Newton was to understand these other forces. In the 19th century, two great British physicists, Michael Faraday and James Clerk Maxwell, solved that problem by once again changing the furniture of reality. Faraday worked in a London laboratory full of bobbins, needles, knives and iron cages, exploring how electrical and magnetic objects attract and repel. He was led to an intuition which is the one upon which modern fundamental physics is based. We mustn't think of forces acting directly between distant objects, as Newton did. We must instead think that there exists an entity diffused throughout space, which is modified by electric and magnetic bodies, and which in turn acts upon the bodies. This entity is today called the field. Faraday sees it as formed by bundles of very thin lines, infinitely thin, which fill space. An invisible, gigantic cobweb filling everything around us. He calls these lines lines of force. They transmit the electric and the magnetic forces from one body to another, as if they were cables pulling and pushing. Thus, two distant charged objects do not attract or repel each other directly, but only via the medium interposed between them. This modification to the world of Newton, this notion of field, is the discovery from which modern physics was born. Maxwell translated Faraday's insight, which Faraday only explains verbally, into a page of equations. These describe the behavior of the electric and the magnetic fields, the mathematical version of the Faraday lines. Maxwell's equations describe all electric and magnetic phenomena. They explain how atoms function, why the particles of the material that forms a stone adhere together, or how the sun works. They are the basis of chemistry and therefore underlie the working of living matter. They describe the force which operates in the neurons of our brain and governs our processing of the information on the world we perceive. And it's this force that turns electric motors and combustion engines, or that allows us to turn on lights and listen to the radio. But there is more. Maxwell's equations tell us what light is. Maxwell realized that his equations predicted that Faraday's lines can tremble and undulate, just like the waves of the sea. He computed the speed at which the undulations of Faraday's lines move, and the result turned out to be the same as the speed of light. Maxwell immediately understood light is nothing else than this rapid trembling of Faraday's lines. Not only have Faraday and Maxwell figured out how electricity and magnetism work, but with the same stroke, as a collateral effect, they have figured out what light is. We see the world around us in colour. Put simply, if the electromagnetic wave of light vibrates more rapidly, the light is bluer. If it vibrates a little more slowly, the light is redder. Light is thus a rapid vibration of the spiderweb of Faraday's lines, which ripple like the surface of a lake as the wind blows. Maxwell recognized that the equations foresaw that Faraday's lines can also vibrate at much lower frequencies, that is to say, slower than light. Therefore, there must be other waves which nobody had yet seen. Only a few years later, these waves, anticipated theoretically by Maxwell, would be revealed by the German physicist Heinrich Hertz. And just a few years later still, Guglielmo Marconi built the first radio. The world had changed, no longer made up of particles in space, but of particles and fields in space. It seemed a minor change, but a few decades later, Newton's world would be shaken even further to its core. In 1905, the definitive proof of the atomic hypothesis put forward by Democritus finally arrived. It was found by a rebellious 25-year-old who had studied physics but had not been able to find employment as a scientist and was making ends meet by working in the patent office in Bern in Switzerland. From observations of granules in fluids, by measuring how much these drift, that is, move away from a position, he calculated the dimensions of their atoms, the elementary grains of which matter is made. Albert Einstein provided, after 2,300 years, the proof of Democritus's insight. Matter is granular. Over the next 2 decades, he was to go on to modify radically and forever the vision of the world. In 1905, at the age of 25, Albert Einstein sent 3 articles to the Annalen der Physik. Each became a pillar of our understanding of the world. In the first, he calculates the dimensions of atoms and proves, after 23 centuries, that the ideas of Democritus were correct. Matter is granular. In the second, he introduces the theory of relativity, known today as special relativity, to differentiate it from his later theory of general relativity. Einstein found his theory of relativity by noticing that the theories of Newton and of Maxwell appeared to contradict each other in a subtle way. Maxwell's equations fix a universal velocity, the velocity of light. But in Newton's physics, the only velocity which exists is the velocity of an object with respect to another object. It is a relative concept. Galileo Galilei had been the first to understand this. But if this is so, then the speed of light determined by Maxwell's equations is velocity with respect to what? Einstein asked himself if there was a way of rendering Newton's and Galileo's core discoveries and Maxwell's theory consistent. In doing so, he showed for the first time that Newton's vision of the world, which had held for 250 years, needed to be radically modified. Between the past and the future of an event, for example, between the past and the future for you, where you are, and in the precise moment in which you are listening to this broadcast, there exists an intermediate zone, an expanded present, a zone that is neither past nor future. The duration of this intermediate zone is very small and depends on the distance from you. At a distance of a few meters from your nose, the duration of what for you is the intermediate zone, neither past nor future, is no more than a few nanoseconds, that is to say, a few millionths of a second, next to nothing. The number of nanoseconds in a second is the same as the number of seconds in 30 years. This is much less than we could possibly notice. On the other side of the ocean, the duration of this intermediate zone is 1,000th of a second, still well below the threshold of our perception of time. But on the moon, the duration of this expanded present is a few seconds, and on Mars it is a quarter of an hour. This means we can say that on Mars there are events that in this precise moment have already happened, events that are yet to happen, but also a quarter of an hour of events during which things occur which aren't either in our past or in our future. They are elsewhere, or maybe elsewhen. We had never before been aware of this elsewhen because next to us this elsewhen is too brief. We are not quick enough to notice it. But it exists. It is real. Say I am on Mars and you are here. I ask you a question and you reply as soon as you've heard what I said. Your reply reaches me a quarter of an hour after I had posed the question. This quarter of an hour is time that is neither past nor future to the moment you've replied to me. The key fact that Einstein understood is that this quarter of an hour is inevitable. It's woven into the texture of the events of space and of time. We can't abbreviate it. In the Andromeda galaxy, the duration of this expanded present is, with respect to us, 2 million years. Everything that happens during these 2 million years is neither past nor future for us. If a friendly advanced Andromeda civilization decided to send a fleet of spacecraft to visit us, it would make no sense to ask whether now the fleet has already left or not yet. The only meaningful question is when we receive the first signal from the departing fleet. From that moment on, not earlier, the departure of the fleet is in our past. The idea of a universal present all over the universe is like the flatness of the Earth, an illusion. We imagined a flat Earth because of the limitations of our senses, because we can't see much beyond our own noses. Had our brain and our senses been more precise, had we easily perceived time in nanoseconds, we would never have made up the idea of a present extending everywhere. We would have realized that saying here and now makes sense, but that saying now to designate events happening now throughout the universe makes no sense. It's like asking whether our galaxy is above or below the galaxy of Andromeda. Above or below has meaning on the surface of the Earth, but not in the universe. There isn't an up and down in the universe. Similarly, there isn't either always a before and an after between two events in the universe. There is a more complex structure called space-time that describes the set of all past and future events, but also those that are elsewhen, neither past nor future. A first result of Einstein's discovery is that as space and time fuse together in a single concept of space-time, so the electric field and the magnetic fields fuse together in the same way, merging into a single entity which today we call the electromagnetic field. There is another implication of the theory, freighted with heavy consequences. Before 1905, two general principles appeared certain: conservation of mass and conservation of energy. The first had been extensively verified by chemists. Mass never changes in a chemical reaction. The second, conservation of energy, followed directly from Newton's equations and was considered one of the most incontrovertible laws. But Einstein realizes that energy and mass are two facets of the same entity, just as the electric and magnetic fields are two facets of the same field, and as space and time are two facets of the one thing, space-time. This implies that mass, by itself, is not conserved. What is conserved is the sum of mass and energy, not each separately. A rapid calculation teaches Einstein how much energy is obtained by transforming 1 gram of mass. The result is the celebrated formula E equals mc squared. Since the speed of light, c, is a very large number, and c squared an even greater number, the energy obtained transforming 1 gram of mass is enormous. It is the energy of millions of bombs exploding at the same time, enough energy to illuminate a city and power the industries of a country for months, or, conversely, capable of destroying in a second hundreds of thousands of human beings in a city such as Hiroshima. The theoretical speculations of the young Einstein had transported humanity into a new era, the era of nuclear power. The impact of Einstein's 1905 relativity paper upon the world of physics was momentous. But we are not yet at his masterpiece. After publishing the theory of special relativity, something troubles Einstein. Special relativity does not square with what was known about gravity. Newton had imagined a force that draws all bodies towards one another, the force of gravity. How this force managed to draw distant things together without anything between them was not understood. 200 years later, Michael Faraday and James Maxwell had added a key missing ingredient to Newton's world, the electromagnetic field. Electric and magnetic force is carried around by electric and magnetic fields. It was clear to Einstein, if not to anyone else at the time, that the solution discovered by Faraday and Maxwell to the question as to what carries the force must reasonably be applied not only to electricity, but also to gravity. There must be a gravitational field, and some equations analogous to Maxwell's capable of describing this field. Einstein immerses himself in the problem. In 1915, he commits to print an article containing the complete solution, the second theory of relativity, which he names the general theory of relativity. It is simple, beautiful, and brilliant. The reason for its beauty is not hard to see. Since antiquity, the idea of empty space, first put forward by Democritus in the 4th century BCE, had troubled thinkers. Newton, who resuscitated Democritus's idea of empty, had tried to patch things up by arguing that space was God's sensorium. No one has ever understood what Newton meant by God's sensorium, perhaps not even Newton himself. Einstein's masterful step is to address not one, but two problems. First, how can we describe the gravitational field? Second, what is Newton's space? And it's here that Einstein's extraordinary stroke of genius occurs, one of the greatest flights in the history of human thinking. What if Newton's mysterious space turned out actually to be the gravitational field? The world is not made up of space plus particles plus electromagnetic field plus gravitational field. The world is made up of particles plus fields and nothing else. But unlike Newton's space, which is flat and fixed, the gravitational field is something which moves and undulates, like Maxwell's electromagnetic field, like Faraday's lines of force. It is a momentous simplification of the world. Newton's space is the gravitational field. Space is no longer different from matter. It is one of the material components of the world, akin to the electromagnetic field. It is a real entity which undulates, fluctuates, bends and contorts. We are not contained within an invisible, rigid scaffolding. We are immersed in a gigantic, flexible mollusk that can be squashed, stretched and twisted. The sun bends space around itself, and the earth acts like a bead which rolls in a funnel. There are no mysterious forces generated by the centre of the funnel. It is the curved nature of the funnel wall which guides the rotation of the bead. Planets circle around the sun, and things fall because space around them is curved. Einstein writes an equation which says that space curves where there is matter. The equation fits into half a line. This is his complete theory of general relativity. But within this equation there is a teeming universe of astonishing predictions, all of which have turned out to be true. Stars burn as long as they have available hydrogen, their fuel, then die out. The remaining material is no longer supported by the pressure of the heat and collapses under its own weight. Einstein's equation predicts that it collapses to the point where it bends space so intensely as to plunge down into an actual hole, a black hole. The theory of general relativity predicts that it is not only space that curves, time does too. Time is not universal and fixed. It is something which expands and shrinks according to the vicinity of masses. The Earth, like all masses, distorts space-time, slowing time down in its vicinity. Einstein predicts that time on Earth passes more quickly at higher altitude. Twins who have lived respectively at sea level and in the mountains will find that when they meet up again, one will have aged more than the other. And further still, the theory predicts that the universe is expanding and emerged from a cosmic explosion 14 billion years ago, the Big Bang, and that the empty expanse of intergalactic space can tremble and wave like the surface of a lake. Gravitational waves, the last and one of the most spectacular of the predictions of Einstein's equation, were observed for the first time in the autumn of 2015. And all of this is the result of one man's elementary intuition that space and gravitational field are the same thing.
1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8.
The two pillars of 20th century physics, general relativity and quantum mechanics, could not be more different from each other. General relativity is a compact jewel. Conceived by a single mind, it's a simple and coherent vision of gravity, space, and time. Quantum mechanics, or quantum theory, on the other hand, emerges from experiments over a quarter of a century. It leads to applications which have transformed our everyday lives. If today we build computers, have advanced molecular chemistry and biology, lasers and semiconductors, it is thanks to quantum mechanics. But more than 100 years after its birth, it remained shrouded in obscurity. In 1900, the German physicist Max Planck tried to compute the amount of electromagnetic waves in equilibrium in a hot box. To obtain a formula reproducing the experimental results, he assumed that the energy of the electric field was distributed in quanta, that is to say, in small packets or bricks of energy, their size depending on the frequency of the electromagnetic waves. This idea was at odds with everything that was known at the time. Energy was considered something that could vary in a continuous manner, and there was no reason to treat it as if it were made up of grains. For Planck, taking energy in finite-sized packets was a trick which happened to work for the calculation, but for utterly unclear reasons. 5 years later, Albert Einstein came to understand that Planck's packets of energy are in fact real. This is the subject of the third of the articles Einstein sent to the Annalen der Physik in 1905, and it won him a Nobel Prize. In the article, Einstein argues that light truly is made up of small grains, or particles. Scientists had observed that certain metals generate a weak electric current when struck by light, the photoelectric effect. The energy carried by light makes the electrons jump out of their atoms. It gives them a push. Einstein uses Planck's idea of the packets of energy with a size that depends on frequency to explain a strange feature of this phenomenon, the fact that it only happens when the light is sufficiently blue, that is, high frequency, and is not dependent, as one would naturally expect, on the quantity of light. Einstein realizes that an electron will be swept out of its atom if the individual grain of light hitting it has sufficient energy. What matters is not the amount of light, that is, the total number of grains of light. What matters is the energy of each grain, and this is determined by the frequency. It's like when it hails. What determines whether your car will be dented is not the total quantity of hail fallen, but the size of the individual hailstones. Similarly, even if there is a lot of light, but formed by grains with insufficient energy, the photoelectric effect will not take place. Today we call these grains of light photons, from the Greek word for light. Photons are the packets of energy of light, it's quanta. The first cornerstone of quantum theory has been established. Physical quantities like energy may come in discrete chunks. Like all offspring, the theory then went its own way. The Danish scientist Niels Bohr pioneered its development. Experiments had shown that an atom is like a small solar system. The mass is concentrated in a heavy central nucleus around which light electrons revolve, more or less like the planets around the sun. Bohr realized that the energy of electrons in atoms could only assume certain quantized values. That is to say, they could exist only on certain particular orbits from the nucleus. Crucially, he made the hypothesis that electrons can only jump between one atomic orbit with a permitted energy to another of the same. These are the famous quantum leaps. Werner Heisenberg was 25 years old when he wrote the equations of quantum mechanics, the same age as Einstein was when he wrote his 3 major articles. Heisenberg's dizzying idea was that electrons do not always exist. That between one interaction with something and another with something else, electrons are literally nowhere. They materialize in a place with a calculable probability only when colliding with something else. An electron is a set of jumps from one interaction to another. The quantum leaps from one orbit to another are the only means they have of being real. This is the second cornerstone of quantum mechanics, the relational aspect of things. In the end, it was another 25-year-old who took the new theory and constructed its entire formal and mathematical scaffolding, the Englishman Paul Dirac, considered by many to be the greatest physicist of the 20th century after Einstein. In his hands, quantum mechanics is transformed into a perfect architecture, airy, simple, and extremely beautiful. Dirac's quantum mechanics is the mathematical theory used today by any engineer, chemist, or molecular biologist. In it, no object has any property in itself apart from those that are unchanging, such as mass. It is not just its position which is undefined, as Heisenberg had recognized. No variable of the object is defined between one interaction and the next. Dirac provides the general recipe to compute the set of values that a physical variable can take. Today, we call this the spectrum of that variable. The theory also gives information on which value of the spectrum will manifest itself in the next interaction, but only in the form of probabilities. We do not know with certainty where the electron will appear, but we can compute the probability that it will appear here or there. This is a radical change from Newton's theory, where everything had seemed to be regulated by firm laws which were universal and irrevocable, where it was possible in principle to predict the future with certainty. Quantum mechanics brings probability to the heart of the evolution of things. This indeterminacy is the third cornerstone of quantum mechanics, the discovery that chance operates at atomic level. The apparent determinism of the macroscopic world is only due to the fact that the microscopic randomness cancels out on average, leaving only fluctuations too minute for us to perceive in everyday life. Shortly after completing the general formulation of quantum mechanics, Dirac realized that the theory can be directly applied to fields such as the electromagnetic one. The notions of fields and particles, separated by Faraday and Maxwell, end up merging in quantum mechanics. Particles are quanta of a field, just as photons are quanta of light. The general form of quantum theory compatible with special relativity is thus called quantum field theory, and forms the basis of today's particle physics. During the course of the 20th century, the list of fundamental fields has been updated, and today we have a theory called the Standard Model of elementary particles, which describes almost everything we see, with the exception of gravity, in the context of quantum field theory. The Standard Model has its limitations. It is convoluted, and there is at least one phenomenon that it does not seem to describe: the dark matter recently detected in the sky by astronomers. But the Standard Model remains the best description we have when speaking about the matter of the world around us. Against expectations, for more than 30 years, every single experiment of particle physics has done nothing but repeatedly confirm the Standard Model. Right now, quantum mechanics offers a spectacularly effective description of nature. The world is not made up of fields and particles, but of a single entity, the quantum field. There are no longer particles which move in space with the passage of time, but quantum fields whose elementary events happen in space-time. We can attempt some conclusions about what it is precisely that quantum mechanics tells us about the world. The first thing we learn is the existence of a fundamental granularity in nature. It isn't the same granularity intuited by Democritus, however. For Democritus, atoms were like little pebbles, whereas in quantum mechanics, particles vanish and reappear. But the root of the idea is still to be found in ancient atomism, and quantum mechanics is a genuine recognition of the profound insights reached by that great philosopher of antiquity. Granularity implies that there is a limit to the information that can exist within a system, that is, a limit to the number of distinguishable states in which a system can be. This limitation upon infinity is the first lesson of quantum mechanics. Secondly, quantum mechanics introduces an elementary indeterminacy to the heart of the world. An electron, a quantum of a field, or a photon appears in a given place and at a given time when colliding with something else. There is no way of knowing with certainty when and where they will appear. The future is genuinely unpredictable. Due to this indeterminacy, in the world described by quantum mechanics, things are constantly subject to random change. All the variables fluctuate continually, as if, at the smallest scale, everything was constantly vibrating. We do not see these omnipresent fluctuations only because of their small scale. If we look at a stone, it stays still. But if we could see its atoms, we would observe them to be always in ceaseless vibration. Quantum mechanics reveals to us that the more we look at the detail of the world, the less constant it is. The third discovery about the world articulated by quantum mechanics is the most profound and difficult, and one which was not anticipated by the atomism of antiquity. The theory doesn't describe things as they are. It describes how things occur and how they interact with each other. It doesn't describe where there is a particle, but how the particle shows itself to others. The world of existent things is reduced to a realm of possible interactions. Reality is reduced to interaction. In a certain sense, this is just an extension of relativity, albeit a radical one. In the world described by quantum mechanics, all variable aspects of an object only exist in relation to other objects. A stone is a vibration of quanta that maintains its structure for a while, just as a marine wave maintains its identity for a while before melting again into the sea. We, like waves and like all objects, are a flux of events. The world of quantum mechanics is not a world of objects, it is a world of events. Quantum mechanics teaches us not to think about the world in terms of things which are in this or that state, but in terms of processes instead. The equations of quantum mechanics do not describe what happens to a physical system, but only how a physical system affects another physical system. A century after its birth, physicists and philosophers continue to ask themselves what the real meaning of the theory might be. An extraordinary dive deep into the nature of reality? A blunder that works by chance? Part of an incomplete puzzle? Or a clue to something profound regarding the structure of the world which we have not properly digested? I think that the obscurity of the theory is not the fault of quantum mechanics, but is rather due to the limited capacity of our imagination. We are on the brink of what we don't know.
1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1.
We now have all the elements with which to understand the current image of the world suggested by fundamental physics. There is a curved space-time born 14 billion years ago and still expanding. Space bends and curves under the weight of matter and plunges into black holes when matter is too concentrated. Matter is distributed in 100 billion galaxies, each containing 100 billion stars, and is made up of quantum fields which manifest themselves in the form of particles, such as electrons and photons, or as waves, such as the electromagnetic ones that bring us television images and the light of the sun and the stars. These quantum fields are strange objects. Their quanta are particles that appear when they interact with something else. Left alone, they unfurl into a cloud of probability. The natural world is a swarming of elementary events, a dance of vibrations immersed in the sea of a vast dynamical space which sways like the water of an ocean. With this image of the world and the few equations that make it concrete, we can describe almost everything that we see. Almost. We now pass from what we know about the world to what we don't yet know, but are trying to glimpse. We are stepping into the unknown. There is a paradox at the heart of our extended understanding of the physical world. General relativity and quantum mechanics are the two jewels that the 20th century has gifted us to help us comprehend the world and today's technology. And yet the two theories cannot both be true, at least not in their present forms, because they appear to contradict each other. Quantum mechanics cannot deal with the curvature of space-time, and general relativity cannot account for quanta. Einstein understood that space and time are manifestations of a physical field, the gravitational field. Niels Bohr, Werner Heisenberg and Paul Dirac understood that physical fields have quantum character, that is to say, they are granular and probabilistic or unpredictable, and they manifest through interactions. It follows that space and time must also be quantum entities possessing these strange properties. This is the problem of quantum gravity. To comprehend what quantum space and quantum time are, we need to change our ideas about reality in order to achieve a coherent vision of the world in keeping with what we have learned about it. A band of theoretical physicists scattered across the 5 continents is seeking to solve the problem. It's not the first time that physics finds itself faced with two highly successful but contradictory theories. Newton discovered universal gravity precisely by combining Galileo's physics of how things move on Earth with Kepler's physics of the heavens. Maxwell and Faraday found the equations of electromagnetism by bringing together what was known about electricity and magnetism. Einstein found special relativity in order to resolve the apparent conflict between Newton's mechanics and Maxwell's electromagnetism, and then general relativity in order to resolve the resulting conflict between Newton's mechanics and his own special relativity. A physicist is only too happy when he finds a conflict between successful theories. It's an extraordinary opportunity. The question to ask is, can we create a conceptual structure compatible with what we have learned about the world with both theories? The scientist who has contributed most significantly to quantum gravity is John Wheeler, a collaborator with Einstein in the United States and a legendary figure who was at the heart of the physics of the entire past century. Quantum gravity manifests itself at an extremely minute scale. Imagine that you are looking at the sea from a great height. You perceive a vast expanse of it, a flat table. Now you descend and look at it more closely. You begin to make out the great waves swollen by the wind. You descend further, and you see that the waves break up, and that the surface of the sea is a turbulent frothing. This is what space is like. On our scale, space is smooth. If we move down to the minute scale, it shatters and foams. Wheeler sought for a way to describe this foaming of space, this wave of probability of different geometries. In 1966, a young colleague of his, Bryce DeWitt, provided the key. Wheeler asked DeWitt to meet him at Raleigh-Durham Airport in North Carolina, where he had a few hours' wait between connecting flights. DeWitt arrived and showed him an equation for a wave function of space, obtained by using a simple mathematical trick. From this conversation, an equation was born which should determine the probability of any curved spaces, the Wheeler-DeWitt equation. The idea is very good, and becomes a basis for the attempts to construct the full theory of quantum gravity, but the equation itself is riddled with serious problems. In the first place, from a mathematical point of view, it's really quite badly defined, but it's also difficult to understand how to interpret it. Among its disconcerting aspects is the fact that it no longer contains the time variable. How can an equation be used to compute the evolution of something which happens in time if it does not include a time variable? What does a physical theory without a temporal variable signify? Dynamical equations in physics always contain the variable t, time. For years, research has revolved around such questions, trying to revise the Wheeler-DeWitt equation in different manners in order to improve it and make it clearer. 20 years ago, the fog was dense. Today, paths have appeared which have elicited enthusiasm and optimism. There is more than one of these, so it can't be said that the problem has been resolved. The path that I consider the most promising is a direction of research called loop theory or loop quantum gravity. General relativity taught us that space is not an inert, empty box, but something dynamic, a kind of immense, mobile snail shell in which we are immersed, which stretches and bends. Quantum mechanics teaches us that every field of this kind is made of quanta and has a fine, granular structure. It follows that physical space, being a field, is made of quanta as well. The same granular structure characterizing the other quantum fields must then also characterize the quantum gravitational field and therefore space. So we expect quanta of gravity, just as there are quanta of light, quanta of the electromagnetic field, and just as particles are quanta of quantum fields. Space is the gravitational field, and the quanta of the gravitational field are quanta of space, the granular constituents of space. The central prediction of loop theory is therefore that space is not a continuum, it is not divisible ad infinitum, it is formed of atoms of space. These are extremely minute, 1 billion of 1 billion times smaller than the smallest of atomic nuclei. Loop theory describes these atoms of space in mathematical form and provides equations which determine their evolution. They are called loops, or rings, because they are linked to each other, forming a network of relations which weaves the texture of space, like the rings of a finely woven, immense, three-dimensional chainmail. Space is created by the linking of these individual quanta of gravity. Space appears continuous to us only because we cannot perceive the extremely small scale of these individual quanta of space. Just as when we look at a t-shirt, we see a continuous piece of cloth, but when we look closely, we see that it's woven from small threads. At an extremely small scale, space is a fluctuating swarm of quanta of gravity which act upon each other and together act upon things. Physical space is the fabric resulting from the ceaseless swarm of this web of relations. But it's the second consequence of the theory that is the most extreme. Just as the idea of a continuous space disappears, so the idea of an elementary and primal time flowing regardless of things also vanishes. The equations describing grains of space and matter no longer contain the variable time. This doesn't mean that everything is stationary and unchanging. On the contrary, it means that change is ubiquitous. But elementary processes cannot be ordered in a common succession of instants. At the minute scale of the grains of space, the dance of nature does not take place to the rhythm of the baton of a single orchestral conductor at a single tempo. Each process dances independently of its neighbours to its own rhythm. There is no longer space which contains the world, and there is no longer time in which events occur. There are only elementary processes wherein quanta of space and matter continually interact with each other. The illusion of space and time which continues around us is a blurred vision of this swarming of elementary processes, just as a clear alpine lake consists in reality of a rapid dance of myriad minuscule water molecules. We must learn to think of the world not as something which changes in time, but in some other way. Things change only in relation to one another. At a fundamental level, there is no time. Our sense of the common passage of time is only an approximation which is valid for our macroscopic scale. It derives from the fact that we perceive the world in a coarse-grained fashion. The backdrop of space has disappeared. Time has disappeared. Classic particles have disappeared along with the classic fields. So what is the world made of? The answer now is simple. Matter is formed by the quanta of fields. Light is formed by quanta of a field. Space is nothing more than a field which is also made of quanta, and time emerges from the processes of this same field. In other words, the world is made entirely from quantum fields. The space and time that we perceive in large scale are our blurred and approximate image of one of these quantum fields, the gravitational field. The separation between the curved and continuous space of Einstein's general relativity and the discrete quanta of quantum mechanics which dwell in a flat and uniform space has dissolved. Continuous space and time are an approximate large-scale vision of the dynamic of quanta of gravity. The quanta of gravity are the way in which space and time interact. General relativity and quantum mechanics are in the end not as incompatible as they seemed. On closer inspection, they shake hands and engage in a beautiful dialogue. The spatial relations that weave Einstein's curved space are the very interactions weaving the relations between the systems of quantum mechanics. The two become compatible and conjoined, two sides of the same coin, as soon as it's recognized that space and time are aspects of a quantum field, and quantum fields can exist even without having their feet on the ground of an external space. This rarefied picture of the fundamental structure of the physical world is the vision of reality offered today by quantum gravity. Little by little, the pieces of the puzzle find their place.
6, 7, 8, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 1.
Today, there is a great deal of talk concerning the possibility that the Big Bang is not a real beginning, that there could have been another universe before it. We know how atoms, elements, galaxies, and stars formed, and how the universe as we see it developed. We know with a reasonable degree of certainty what happened on a large scale to our universe in the last 14 billion years, from the time when it was a ball of fire. But what happened before this initial hot and compressed state? At that point, we enter into the realm of quantum gravity. Let us imagine a universe contracting and becoming extremely small, squashed by its own weight. If we take quantum mechanics into account, the universe cannot be indefinitely squashed. A quantum repulsion makes it rebound. A contracting universe does not collapse down to a point. It bounces back and begins to expand, as if it were emerging from a cosmic explosion. The past of our universe could therefore well be the result of just such a rebound. A big bounce instead of a big bang. This is what seems to emerge from the equations of quantum loop gravity when they are applied to the expansion of the universe. The image of the bounce mustn't be taken literally. In the crucial passage through the big bounce, we can no longer think of a single, although granular, space and time. At the big bounce, the world is dissolved into a swarming cloud of probabilities, in which time and space wildly fluctuate. Our universe could be the result of the collapse of a previous collapsing universe passing across a quantum phase where space and time are dissolved into probabilities. The word universe becomes ambiguous. If by universe we mean all that there is, then by definition there cannot be a second universe. But the word has assumed another meaning in cosmology. It refers to the space-time continuum that we see directly around us, filled with galaxies whose geometry and history we observe. There is no reason to be certain that, in this sense, this universe is the only one in existence. We can reconstruct the past up to the time when the spatio-temporal continuum breaks up like sea foam and fragments into a quantum cloud of probabilities. We should not discard the possibility that beyond this hot foam there could be another spatio-temporal continuum similar to the one which we perceive around us. All of this is still at an exploratory stage, but what is remarkable in this story is that today we have equations with which to try to describe these events. If we have the equations that describe the transition of the universe across the quantum phase, we can compute effects of quantum phenomena upon the universe which we observe today. The electromagnetic field in the immense space between galaxies is not null and inert, but trembles like the surface of the sea after a big storm. This quivering, disseminated throughout the universe, is called the cosmic background radiation. The details of the structure of this radiation tell us the history of the universe, and hidden in the folds of these details there could be footprints of the quantum beginning of our universe. One of the most active sectors of research in loop quantum gravity is the study of how the quantum dynamic of the primordial universe is reflected in this cosmic background radiation data. The results are preliminary but encouraging. The situation is still fluid, but those who, like myself, have spent their lives seeking to understand the secrets of quantum space are following with close attention the continuous honing of our capacity to make observations, to measure and to calculate. And we are awaiting the moment in which nature will tell us whether we are right or not. Traces of the great primordial heat must also be in the gravitational field. The gravitational field, that is to say, space itself, must be tremulous like the surface of the sea. Therefore, a cosmic gravitational background radiation must also exist, older even than the electromagnetic one, because the gravitational waves are disturbed less by matter than the electromagnetic waves, and were able to travel undisturbed even when the universe was too dense to let the electromagnetic waves pass. In the subtle irregularities of space, we should be able to find traces of events which took place 14 billion years ago, at the origin of our universe. And when we do, we should be able to confirm our deductions on the nature of space and time. I've described what I think is the nature of things in the light of what we have learned to date. Am I sure about all this? I'm not. One of the very first and most beautiful pages in the history of science is the passage in Plato's Phaedo in which Socrates explains the shape of the earth. Socrates says he believes the earth is a sphere with great valleys where men live. He's basically right, if a bit confused. He adds, I'm not sure. This acute awareness of our ignorance is the heart of scientific thinking. It's thanks to this awareness of the limits of our knowledge that we have learnt so much. We're not certain of everything that we suspect, just as Socrates was not sure of the spherical nature of the earth. We are exploring at the borders of our knowledge. Awareness of the limits of our knowledge is also awareness of the fact that what we know may turn out to be wrong or inexact. To learn something, it's necessary to have the courage to accept that what we think we know, including our most rooted convictions, may be wrong, or at least naive. Science is born from this act of humility. We learn nothing if we think that we already know the essentials, if we assume that they were written in a book or known by the elders of the tribe. The centuries in which people had faith in what they believed were the centuries in which little new was learned. If they had trusted the knowledge of their fathers, Einstein, Newton, and Copernicus would never have called things into question and would never have been able to move our knowledge forwards. Science is sometimes criticized for pretending to explain everything, for thinking that it has an answer to every question. It's a curious accusation. As every researcher working in every laboratory throughout the world knows, doing science means coming up hard on a daily basis against your ignorance, your limits, and the innumerable things which you don't know and can't do. But if we are certain of nothing, how can we possibly rely on what science tells us? The answer is simple. Science is not reliable because it provides certainty. It's reliable because it provides us with the best answers we have at present. Science is the best we know about the problems confronting us. It is precisely its openness, its constant putting current knowledge in question, which guarantees that the answers it offers are the best so far available. If you find better answers, these new answers become science. The answers given by science, then, are reliable because they are not definitive. We don't consider them to be definitive because they are open to improvement. Though rooted in previous knowledge, science is an adventure based on continuous change. The story I have told is a story with roots that reach back over millennia, a story that has treasured good ideas, but hasn't hesitated to throw ideas away when something which worked better was found. The nature of scientific thinking is critical, rebellious. It is dissatisfied with a priori conceptions, reverence, or untouchable truth. The search for knowledge is not nourished by certainty. It is nourished by a radical distrust in certainty. This means not giving credence to those who say they are in possession of the truth. For this reason, science and religion frequently find themselves on a collision course. Not because science pretends to know ultimate answers, but precisely for the opposite reason, because the scientific spirit distrusts whoever claims to be the one having ultimate answers or privileged access to truth. This distrust is found to be disturbing in some religious quarters. It is not science which is disturbed by religion. There are certain religions that are disturbed by scientific thinking. To accept the substantial uncertainty of our knowledge is to accept living immersed in ignorance and therefore in mystery. To live with questions to which we do not know the answers. Perhaps we don't know them yet, or, who knows, we never will. To live with uncertainty may be difficult. There are those who prefer any certainty, even if unfounded, to the uncertainty which comes from recognizing our own limits. There are some who prefer to believe in a story just because it was believed by the tribe's ancestors, rather than bravely accept uncertainty. To accept that we live without knowing everything that we desire to know. Ignorance can be scary. Out of fear, we can tell ourselves reassuring stories, something that calms us. There are many people, many institutions who offer comforting answers. There is always someone who has the presumption to be the depository of truth, neglecting to notice that the world is full of other depositories of truth, each one different from that of the others. For my part, I prefer to look our ignorance in the face, to accept it, and to seek to look just a bit further, to try to understand that which we are able to understand. Not just because accepting this ignorance is the way to avoid being entangled in superstitions and prejudices, but because to accept our ignorance in the first place seems to me to be the truest, the most beautiful, and above all, the most honest way. To seek to look further, to go further, seems to me to be one of the splendid things which give sense to life, like loving or looking at the sky. The curiosity to learn, to discover, to look over the next hill, the desire to taste the apple. These are the things which make us human. The world is more extraordinary and profound than any of the fables told by our forefathers. I want to go and see it. To accept uncertainty doesn't detract from our sense of mystery. On the contrary, we are immersed in the mystery and the beauty of the world. The world revealed by quantum gravity is a new and strange one, still full of mystery, but coherent with its simple and clear beauty. It is a world which does not exist in space, and which does not develop in time. A world made up solely of interacting quantum fields, the swarming of which, through a dense network of reciprocal interactions, generates space, time, particles, waves, and light. Quanta of space mingle with the foam of space-time, and the structure of things is born from reciprocal information which weaves the correlations between the regions of the world. A world which we know how to describe with a set of equations, perhaps to be corrected. It's a vast world with much still to clarify, to explore. There are frontiers where we are learning, and our desire for knowledge burns. They are in the most minute reaches of the fabric of space, at the origins of the cosmos, in the nature of time, in the phenomenon of black holes, and in the workings of our own thought processes. Here, on the edge of what we know, in contact with the ocean of the unknown, shines the beauty and mystery of the world. And it's breathtaking.